www.nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Okay, so I also, when we talk about the microscope, one of the most important things is that we have to do all this in vacuum. And it's been my experience in introductory level and even beyond in the TEM and in the SEM2, which is the next class you may take. Most of the problems people have to do with vacuums, right? Getting the sample in and having the vacuum crash. Having stuff come off the sample and the vacuum crash. Having the vacuum crash because of a problem. And so one of the things I want to do is just give you a one lecture sort of overview of vacuum science, because I think it'll help you throughout your graduate careers, and also maybe will help you analyze problems and cause us less problems as well. So just a short overview of vacuum science, appallingly short. Okay. What I want to do is just give a very brief overview of some of the concepts in vacuum science, with a focus really on how pressure determines contamination, because that's the thing we're most interested in. We'll talk a bit about the types of gauges and the types of pumps, and then I'll walk you through the typical vacuum system that was used in the TEM, something like the one on the 2000 FX. Again, we have to have everything in vacuum, because if we have too much gas in the microscope, then what happens is the electrons can't make it down through the microscope and to hit your sample, right? They'll scatter off of the gaseous atoms that are there. And so generally the idea is to use a relatively high level of vacuum, something around 10 to the minus 7. That allows you to have no extra scattering from gas. It also keeps the samples clean. One of the problems that can happen is if your samples have excess hydrocarbons on them from things like your finger grease when you were making the sample, glues when you were making the sample, those things can become problematic. They'll tend to agglomerate where the beam is, and so it's good to have a good vacuum for lots of reasons, all right? So really those are the two reasons that we care. It's to make sure that we have a reasonable vacuum so we don't have too much scattering in advance of and after the interaction with the sample, and also we worry about the contamination. I think pressure units are a complete mess. What happens is that most people I know talk in torr. Unfortunately, that's a no-no unit, right? We're supposed to talk about things in pascals because that's SI. If you tell me that something's at 10 to the minus 3 Pascal, I have absolutely no meaning to that, so I'll talk in torr. The way to kind of remember is there's about a 10 to the minus 3 difference, so if you read 10 to the minus 3 Pascal, it's about 10 to the minus 6 torr. But again, it's a problem. Millibar and torr scale sort of together. Again, other vacuum gauge companies will use millibar. The different ranges of vacuum we tend to call low vacuum or poor vacuum being low vacuum, something between room pressure and about 1 torr. Medium vacuum about 1 torr to about 10 to the minus 3 torr. High vacuum 10 to the minus 3 to 10 to the minus 7 or 8. And then ultra high vacuum 10 to the minus 9 or better. But if you talk to people who do surface science, they'll tell you that that vacuum's terrible and you need to be at least in the low 10 to the minus 10s to really consider it ultra high vacuum. And the thing is to do low vacuum, to do high vacuum, to do ultra high vacuum requires substantially different types of instrumentation, different types of pumps, different types of care with respect to sealing things. And so the compromise that is most usually made in the TEM world is to focus on creating around the sample high vacuum and give up on the extra effort of going to ultra high vacuum, okay? The gains aren't really worth it in the end. There's a couple of UHV machines out there. They're mostly used to do surface science in odd and interesting ways. An appallingly brief introduction to vacuum, right? What you can do is you can use the kinetic theory of gas to go through and do a couple derivations. Really, the idea of pressure, of course, is that if you have a container, you've got molecules in the container. As you have higher pressure, you either have more molecules or faster molecules running into the walls and providing some force against those walls, and that's what you measure as pressure. If you want, you're welcome to do this on your own. You can go through and look at things like what's the flux of particles into the wall, what's the mean free path of a particle as a function of pressure. This one's a useful one to think about because really what you're getting is as you go to lower and lower pressures, the relative distance a molecule travels before it scatters goes up. That's useful to know, right? And so what that means is if you have relatively low vacuum, your molecules are able to move around quite freely without impacting each other. But the most important thing in all of this is that in our world, we worry mostly about contamination rates. And so if you go through and look at how long it takes in terms of time to form a single atomic layer of contamination, this scales with pressure. It scales with pressure via this impingement time there. But really you can go through and make a direct conversion between the measured pressure in the system and how quickly you are getting contamination. And so if you are at atmospheric pressure, you are getting a single atomic layer of contamination every nanosecond, okay? If you're working down at the 10 to the minus 6 torr regime, which is a little bit worse than we'd like to be in the TEM, it's about 1 second. In the case of 10 to the minus 8, it's about 100 seconds. Now, so we work at around 10 to the minus 8. You tend to look at regions of the sample for more than 100 seconds. So what that means is you will get some contamination of your sample even in a good vacuum in your TEM. The thing that really is better is if you go down to the very low levels of vacuum, you get relatively low contamination rates. And so it's something like 10 to the minus 10 torr, it's about 3 hours. And that's why the surface science people, the people that are trying to look at clean surfaces and understand their structure and properties, really focus on things down in the low 10 to the minus 10 torr. So I remember this number myself. I remember 1 second at 10 to the minus 6 torr, just because it helps me know how bad the vacuum is, okay? So it's just the number that 1 second, 10 to the minus 6 torr. Stick that in your brain for later usage. Okay, that's all the vacuum stuff I want to go over in terms of the theory and basically none of it, but just knowing that if you have relatively variable pressure, you get relatively variable rates of contamination or monolayer formation time. I'll go through the working of a couple vacuum gauges because these are your eyes into what the pressure is in your system. For relatively low pressures, things between room pressure and down to minus 10 to the minus 4 torr, we use what's called a Pirani gauge. And really the idea here is that you use a heated wire filament. You put that wire filament in the center of a Wheatstone bridge so that you can sensitively detect changes in the resistivity. And what happens is as you change pressure, right, you get different particles impacting that wire filament and carrying different levels of heat away from it, okay? And so as you have a higher and higher pressure, the temperature of that thing will change, the resistivity of that wire will change, and you simply calibrate pressure versus resistivity to give you, you measure the changes in resistivity with a known pressure, and then when you stick it into your system, you have then an ability to broadly say that as this changes a given amount of resistance, you've got a given amount of change in pressure. It is not highly accurate, but they were pretty robust, and they're the things that we use to get just a general level of vacuum. In the case of the TEM, we're always trying to work well below 10 to the minus 4, so the only time you ever really interact with these things is when you've had a problem, right? And you are up at air and you're trying to pump your system down. You use the Pirani gauge to go, okay, looks like it's going the right direction. Yep, going down, going down, going down into the 10 to the minus 4. And then at that point, other pumping systems will kick on to pump down to lower and lower levels of vacuum. Okay, so it's really just a gauge to see, am I going the right way and am I getting towards okay vacuum? The ones that we use more often are the cathode gauges. There's the hot cathode, the cold cathode, I'll explain as well. The idea here is that when you get down below 10 to the minus 3 or so, it gets difficult to detect pressure directly. You no longer have a sufficient number of particles to cause a change in temperature that's readily measurable. In the case of the Pirani gauge, there's no real direct measurement of the forces that are involved because they're relatively small. And so what people instead do is they use an indirect reading. And the idea here is you use a filament, just like we would use a filament in the case of thermionic emission in the TEM. You use a filament to have electrons come off. You accelerate them across a collection, across a grid and to a collector. And basically, as you go through and have different levels of gas here, you get these things impacting these gas molecules. These will ionize as a result of that impaction, and you'll collect on the other side a current that's correlated with the relative number of the molecules that are present. And so it's an indirect reading. You're really kind of counting particles instead of directly measuring pressure. But the thing about them is that they have a good range. They're pretty robust. They operate, in medium vacuum down to pretty high vacuum. They're not particularly accurate, but in the end, you don't care, right? Because your goal is to make sure that your vacuum system's working. And so you turn the thing on, you use the Pirani gauge, it gets better down to 10 to the minus 4. Your other things kick in, your better vacuum pumps. It continues to pump down to, okay, bottom of the range, and you're happy, okay? You don't care so much if it's 1 times 10 to the minus 8 or 5 times 10 to the minus 7. You just know that that's what you're going to get out of your system. So they work pretty well. If you want a more accurate gauge, people tend to use the Penning gauge or the cold cathode. It's the same idea. You use a similar mode of ionizing the gas and counting the particles. But what you do is you also put the electrons in the presence of a magnetic field. This causes them to spin around. They have a longer path length, and that leads to a greater sensitivity and detection. And so these things give you between 10 to the minus 2 and 10 to the minus 11 torr type of sensitivity. So you will see cold cathode gauges used, largely up in the gun area. You'll see hot cathode used throughout the microscope. You'll see Pirani gauges used as well. And those are the primary types of gauges that we use in the TEM. A mechanical pump, of course, this is one of the most common pumps to see lying around. There's 2 primary types that are used. There's the rotary pump, and there's now the scroll pump. Rotary pump, they're very nice pumps. They are inexpensive. They work well. The idea with these is that you are basically taking an air inlet. You have a rotor that goes around, and it just kind of squeezes the air out the other side, okay? So it's off symmetry in its rotation, and as it rotates clockwise here, it basically traps the air here and then pushes it out the other side, okay? Very simple mechanism and the like. They work very well for ambient to 10 to the minus 3 torr. These things are called roughing pumps or rough pumps because they're just getting rid of most of the gas when initiating the vacuum sequence. Now, some disadvantages to some of the rotary pumps is that they are oil-based and they can be dirty and loud as a result. Also, the mechanism that they're using, it can introduce vibration. So in the microscopy world, if you use one of these things and you have a fairly high resolution microscope, this thing will sit quite some distance away, preferably on a different piece of concrete slab than your microscope. And so this is something to be concerned with. Now, because they have oil in them, there are increasing drives within the semiconductor industry to get rid of all oil-based pumps throughout the systems. And so most of the microscopes you buy these days will forego the regular rotary pump and instead use a scroll pump. The idea of a scroll pump is it is oil-free. It works like a turbo pump, which I'm going to talk about next. But basically, it's just a bunch of rotors that the idea is that they spin around again, much like the roughing pump. They trap air in here, and then by their spinning, the air is forced down through this kind of curlicue, looks like a cinnamon bun, right, and into the output so that they get passed through. And the thing about these is that they are cleaner, they have less vibration, and really they're a better system for microscopy purposes because of this, and are becoming more and more the standard that you buy as you purchase a new TEM, okay? And the roughing pump, its major goal is 2 things. It is used to initiate the vacuum. If you put your microscope in, right, or you've had a problem over the weekend or whatever, where you're not at vacuum, the first thing that goes on is your roughing pump, and it removes most of the gas, takes you from 760 torr down to 10 to the minus 3 torr, and just gets things going. And then the other use of the roughing pump is often it sits on the other side of, say, a turbo or a diffusion pump, one of the higher vacuum pumps, and is used to back off and remove the output of those pumps out to air, okay? So it forms part of a system in that regard, and we'll see how that all goes together. Another type of pump that is used less frequently these days, the older microscopes have them. Again, some of the ones we'll use downstairs have diffusion pumps. The idea here is that what you do is you take a oil, shown here on the bottom, you heat that oil until it vaporizes, that oil vapor rises, and then comes through these little outlets and condenses down on the cold side here. And so if there's gases floating around, the oil molecules will basically impact upon those gas molecules and force them down into the area that is the outlet. And so you have, again, a ability to pull vacuum from top in an inlet to an outlet. The idea, again, that this is having these oil molecules that are condensing down and knocking the gases down physically via kind of an interaction through here. Now, the thing about the diffusion pump is, again, it's oil-based. And so if for some reason you screw up the vacuum order, right, you hit the wrong button in the wrong order, and you put a positive pressure here with respect to there, you can have oil go back up into your system. This can be disastrous, and as a result, most of the systems that use these diffusion pumps do not let you do anything with the vacuum other than initiate it, okay? In the case of the 2000 FX downstairs, that can cause some delay, because if you have a problem, it always goes through a 25-minute cycle where it heats, quote-unquote, heats the oil before initiating vacuum and opening it up to the machine, even if the oil is already hot. So if you have a short vacuum problem, right, you still have to wait that 25 minutes, and you cannot override it because they don't want you to have the ability to put the wrong pressure on that side of that thing and squirt it back up into the column, okay? Now, diffusion pumps are nice. They're very efficient. They are vibration-free, right? There's no moving parts. And so you could stick a diffusion pump straight on your column and not have it affect the resolution. That's great. The oil problem is something that people are worried about. And so again, as the more modern microscopes mostly skip the diffusion pump, but you'll still see them. They're capable of going down to very low vacuums. They can go from 10 to minus 3 all the way down to 10 to minus 11 torr, so they can be used for high vacuum applications. But of course, one thing to remember is that's only something that you can achieve if your entire system is tight enough to get to 10 to the minus 11 torr. And so most microscopes use rubber seals throughout, and only can get down to the 10 to minus 7, 10 to minus 8 regime. They don't use copper gasket seals and the like. But again, diffusion pumps usually work pretty well. In those systems where you're using or trying to get to ultra high vacuum, people just never use a diffusion pump, because if you have backstreaming once, you will basically never get to UHV again in that system. So it's a choice that was made years ago and is increasingly being phased out for the electron microscopy world. But they're still pretty nice pumps for certain applications. The more common way to do things now is through a combination of turbo pumps and ion pumps to get the highest level of vacuum. The way that a turbo pump works, this is a picture of the main rotor blades in here, and the idea is to spin this thing very, very, very fast. If you have an inlet side and an outlet side, the idea is that if you have gas come in, it will just physically bounce off of one of these blades and bounce back, and if this thing's spinning fast enough, right, it will always get captured and pushed out through the other side, okay, just by the action of this thing moving this way while the gas comes in. And so it's just a mechanical removal of the gaseous ions, or the gaseous molecules that you don't want. And so the idea is that you're just going through and spinning this thing so fast that you capture things. Anything that comes in the inlet will bounce its way back. And basically you see that it has different angles on this as you go from the top to the bottom, and that's just to get a more efficient pumping of the smaller amounts as you go out. The turbo pump is relatively vibration-free in terms of things. You can use a turbo pump and still get to pretty good levels of resolution, but you have to isolate the thing pretty carefully. And so when you look, your turbo pump will be on top of a couple big rubber gaskets and attached to a frame so that you don't end up introducing much vibration from this thing spinning around into your microscope column. They're also quite good pumps. You can go from something like ambient if you want, down to 10 to the minus 9 torr. Usually people do not go from ambient. Usually they rough the thing out to 10 to the minus 3 first, and then go down to 10 to the minus 9 torr thereafter. You will generally use these in combination, as I say, a rough pump first and then turn on the turbo and back it off. But you can get to pretty good vacuum pretty quickly with a turbo pump. They're a pretty nice way to go. Now, the turbo pump again gets you down into the sort of level of work that you want to do. But then if you are trying to do the highest levels of resolution, you may not want that possibility of having vibration at all. And so what people will do thereafter is use an ion pump to get down to the final levels of pressure, and also to use the system without having too much possibility of vibration. An ion pump is a pump that uses no moving parts. The idea here is that you have basically this box that has an anode and a cathode. You have a system of ions that will come off of this anode and cathode as you go through. You're basically having a field emission or a thermionic emission process where these things are coming out. And then you use a magnetic field to spin these things around so that these ions are moving around. And if they encounter a gas molecule, what will happen is they'll knock them into the walls of the ion pump where they stick. And usually what you do is you coat the walls with titanium. You do this once a day so that there's a nice fresh coat of titanium for things to stick to. And the idea is you just permanently trap them in that regard. The ion pump doesn't turn on until you get down to 10 to the minus 5 torr, but it can work down to 10 to the minus 11. And so if you're working in the UHV, this is a very good type of pump to use. But again, you have to go through and first use a roughing pump and then a turbo pump to get down into the 10 to the minus 5 sort of a regime. Usually in the modern TEM, you'll be using ion pumps up in the gun all the time. You'll use ion pumps local to the sample after you've gone through and introduced the sample and used the turbo to back everything, the combination of the roughing pump and the turbo to back everything out. And again, these things have no vibrations, so they don't interfere with your work in terms of moving the column around and shaking your atoms that you're trying to take a picture of, okay? So those are the four primary pumps that you'll see in the TEM. You'll see roughing pumps all the time. Increasingly, you will not see diffusion pumps, but instead see combinations of roughing and ion pumps. The advantages with the roughing and ion pump, again, is that using that in that combination reduces the possibility of both vibration as well as having a vacuum problem associated with the oil going the wrong way. Now, if you start adding a bunch of turbo pumps and a bunch of ion pumps onto your machine, it gets expensive. That's one of the reasons that the modern microscopes are increasingly expensive, is that if you're doing something like a field emission source, you have to have very good vacuum. You put a number of ion pumps up near the source, and it adds up with time. Okay, so it's one of the things that makes these things cost a fair amount. Another thing that people use in the electron microscopy world very frequently to help with the vacuum is they'll use some form of cryopumping, or in the case of the microscope, usually what you're doing is you have a little metal cold finger, they call it. It's just a little piece of metal that's very close to your sample, and you cool that with liquid nitrogen. And the idea is that if you have stuff that's floating around your sample, it'll look at that cold surface and prefer to go there through one of these mechanisms and stay there, thereby keeping that area right around your sample very clean through the use of this additional pumping mechanism, cryosorption or the like. There's three types of things that can happen. You can have cryocondensation. The idea there is that the molecules that are floating around will condense on sites on that surface, and you can go ahead and increase the time that they'll stay there by just having a colder and colder surface. You can have cryosorption. That's where you're having van der Waals attractions hold the molecules, or you can actually just have the molecules trapped by the frozen bits that are there on top of the cold finger itself. In the case of the electron microscope, we use this in two major ways. In the modern microscope, it's usually called a cold finger or an anti-contamination device. It's just a little piece of metal that sits near the sample, gets cold, and is used to pump that region locally. In the case of older microscopes, especially diffusion pump systems, people would often add in an additional liquid nitrogen bath near the main column to help pull the vacuum down. Now, the thing about this is if the cryo cold finger warms up, then those extra molecules that you trap that way will go away. And so if you're working on the microscope and using the cold finger, you have to keep it cold by supplying liquid nitrogen, usually every couple of hours or so. And then at the end of the day, what you do is you take your sample out and you do a specific sequence where you warm that thing up to get rid of all the stuff that was stuck there while you were operating the microscope. Usually what will happen is you'll hit a button and it'll say, okay, I'm going to shut the ion pumps off, turn the turbo pumps on, and then heat this thing up so that all the residual things now go out the turbo, right? And you do that for a couple of hours, and then the system turns itself back to the state of having the ion pump in. So it's all organized for you when you hit a button on the modern system, okay? Yes, sir?
Pressure range, is there affected that or not affected that?
Pardon me?
Is there a particular range, like you mentioned these were done, or each pump had an effective range?
Right. This is one, so yeah, so the question was, what's the effective range for doing this? Usually you only do this once you've got your sample, you know, it's the same time you're inserting your sample, and it's used to keep things down into the low 10 to the minus 7, maybe even at the high 10 to the minus 8s, within the very local region to your sample. And it's just pumping, it's just using this extra cold finger to work right there after you've already got things pretty good shape, okay? And I like them. They're kind of a pain in the neck, but they do help a little bit. So, and the real reason for this is that once you're at 10 to the minus 6 torr or whatever, you don't have to worry much about your electrons scattering off gases in the column. You're really now more worried about contamination on your sample, extra stuff that came in with your sample, like your finger grease, which is usually what it is. And so the idea here is if your electron beam's coming in, it causes some of that extra contamination to get put up into the vacuum off of the surface. Then instead of going back down where you're looking, it may go over to this cold finger. And so that's really what it's primarily being used for, is to take care of additional contamination. Okay? So when you use the microscope, there will be a dewar, that you go and pump the liquid nitrogen out of, fill the thing in right next to the microscope. It hangs right off of the microscope, and you'll learn how to do that as you do. Liquid nitrogen, right? You need to use glasses. You need to use gloves. No open-toed shoes. Your Birkenstocks are not appropriate for pouring liquid nitrogen in because you can burn yourself with it. Okay? That's me being safety manager. But also accurate. You need to be a little bit more careful with that. Okay? So how does all this stuff go together? This is a diagram taken again from the Williams and Carter book, just showing a kind of a hypothetical vacuum system. And what I want to do is run through how you would start. Let's pretend that you have had no vacuum in your microscope at all. You just moved it from the material science and electrical engineering building over to Armstrong, okay? So the idea is that you need to turn the vacuum system on. The first thing that you will do is you will turn on this mechanical pump, the roughing pump, the scroll pump, whichever you have, and this thing will pump along the line on the right, and at some point you will open up valve number 1 here, which will allow you to evacuate the TEM column through the rough pump. And you will go from air pressure, 760 torr, down to the 10 to the minus 3 regime. Second, what you'll do is you'll turn on the diffusion pump, okay? And you will let that thing warm up so that the oil gets hot and it begins to work. That will take some period of time, and again, most microscopes will force you to wait the correct amount of time. You will also, during that time, usually open valve number 2 so that you do 2 things. You will pump on the back side of this diffusion pump so that if there are things coming out as this thing warms up, you again have a way to take them out so they don't just jam up in the diffusion pump region. You'll also pump on what's usually called the reserve tank or vacuum reservoir, and this is just a big empty volume that you pump out so that if there are hiccups or problems along the way, there's a place for gases to go in addition. It just helps by having an empty area for extra gases to go. Okay, so that's called the reserve tank. And again, I'll show you where that is on the main vacuum page of the microscope. So once your diffusion pump is oiled up, is ready to go, you'd open up number 3 and pump the column down to the 10 to the minus 6, 10 to the minus 7 regime. If instead you had roughing pumps and turbo pumps, the system would be a little bit more complicated. You would instead turn on the turbo pumps, use those to evacuate down to the 10 to the minus 7 sort of regime, and then turn them off, open up the valve to the ion pump, and then use the ion pump during normal operation. Okay? So it just depends on which system you have. So it's a multiple part process where you use one pump to go in one range of vacuum, the low vacuum. You need to get down into the medium vacuum, and then preferably towards the high vacuum regime with either the diffusion pumps or the ion pumps doing that work because they're vibration free. Every microscope has a different vacuum system, and when you start to use a microscope, you need to go through and look at the diagram that's associated with that microscope, and usually the thing on the left comes from the manual, the thing on the right comes from the little screen that we have as our interactive gauge with the microscope as we use it. What you want to do is go through and figure out, okay, what pumps are where? Okay, so we have DP, and they have, okay, a diffusion pump here, diffusion pump 1, diffusion pump 2. RP, roughing pump. There are different gauges, the Penning gauges, the Pirani gauges. There's the vacuum reservoir, the oil rotary pump, all the different things. And then there's also these little bow tie looking things are usually the way that we describe the valves, and it'll tell you what is considered open and what is considered closed, whether or not this is full or empty. And so it's helpful to figure out, okay, here's the viewing chamber. What things can pump on the viewing chamber? Well, what we can see is that the roughing pump If valve 10 is open and valve 9 is open, we'll pump on the viewing chamber. Okay? Also, if valve 13 is open and my diffusion pump is on, and either V6A or V6B is open, that will pump on the viewing chamber. Okay? It turns out that V6A and V6B, this is a bigger opening and a smaller opening, I believe. And I think the idea here is that if you are still trying to pull this thing down to vacuum, you first use this one, and then you switch to that one so that you lower the load on this pump and can use it to back up this diffusion pump as the thing works. Okay? Anyway, there's a fair amount of complication in all of this. In terms of watching all of these things. But what's nice is that this thing updates itself continuously on the microscope, and it's actually a bit simplified over here. So again, if you were to turn the thing on, all of the valves would be closed. The first thing that would go is your roughing pump, shown at the bottom with a little hole there, would turn on, and you would start to evacuate the main column through valve, say, V9. Okay? And then you would turn on the oil pump, the diffusion pump, first back that out, and then use those. It's only showing one diffusion pump, even though there are in fact two, and use those to do the primary pumping down there. There's listing of pressure gauge readings on the modern microscopes. Those will be in Tor. In the case of the 2000 FX, they just read the currents running through those gauges. Lower current, better vacuum. Okay? And so you just learn for your own microscope which things need to be at which level in order for things to be operating properly. Yes, sir?
Lab 1, you accidentally hit one of the valves.
Yeah, actually in Lab 1 for one group, on the 2000 FX, the camera chamber, there's a little lever to open up the film camera, and it's not too far from your knees. And I banged it with my knee and opened that up. So what that does is it initiates a sequence. And that sequence says, okay, I'm being told that I want to take the film out. So it shuts valve 3, right, so that we don't have any possibility of air leaking up into the column. It shuts valve 2, so that for sure nothing will get up to the gun. And then it starts to, often they'll show the nitrogen, it doesn't in this case, but usually what happens is they will start to flow nitrogen in order to vent the thing. You usually vent with nitrogen instead of air because it's a bit cleaner. Air has water. If you pump in nitrogen first, that absorbs to the walls and is easier to pump down after that. But what I did is just accidentally initiate that cycle. And so I said, oh, wait, the beam's gone. And then you look and you realize that's what you've done. You put the thing back, and you'll recall it took just a minute or two, right? Because it was actually already in pretty good vacuum. It hadn't evacuated yet. And then, first it checked with the roughing pump, and then it checked with valve 6A, right? And then 6B. You might even remember we watched that sequence go through. Okay? So I will probably do that in lab for everyone. Initially, do that in the way that you start to see some of these things move around. Again, on the older system we have downstairs, I just checked, it's actually 21 years old at the moment, okay? So we're finding that the goniometer is getting a little leaky, so sometimes we have problems there. So when you put the sample in, what you first do is you pump with the roughing pump on the sample region so that you don't introduce air straight in, right? And then when that gets good, you go ahead and put a little bit of air, the 10 to the minus 3 volume in, and it pumps away from there, okay? I think that's the way the 2000 FX works. In the case of the Titan, instead, because it's just, again, more modern, they first go through and pump it out with a turbo and bring that down even better to get a cleaner column. But all these things are worth following, and we'll watch through this. Again, the reason that I teach this little section of this class is because I found in my old job, where we didn't have this class, the vacuum confused people, and the simple things like what's going on, why is it that I'm not seeing the beam? People didn't think, well, I should look at the vacuum system and figure out what it's doing. Maybe something's not right. And so I think if you have just these basic concepts of vacuum and some realization that it's just a diagram that you're reading and trying to understand what's doing what, it helps you make sure that you can run the machine more efficiently and have less problems and less downtime. Again, I've mentioned this, the reason that we really get to the low levels of vacuum is contamination. It can be a real problem, and it can affect your results. So I want to talk about it in a couple ways. This is one example from something I was doing. I was trying to look at the growth of these little holes in gallium nitride. If you have a screw dislocation in gallium nitride, it may have an empty core. It does this to relieve the strain associated with the large Burgers vector of that dislocation. And so I was doing a bunch of experiments where I was holding it at time, for various amounts of time at high temperature and watching those things grow to characterize the kinetics of that. And this was an experiment, you can see, first I checked the beam area, said, oh, I've got a good area, right? and then I focused in right here with a beam size of or an overall spot area of about a micron in diameter, and I spent a day, right, with 30 minutes at different temperatures, all focused right here, okay? Got a lot of really good data. I'm really happy about it. I finished my day, and of course, a part of routine of shutting the thing down, I go to a low level of magnification so I can leave it for the next person in the right place. And what do I notice? I notice 3 separate regimes, right? One of which where there had been no imaging with the electron beam, one of which where there had been a little bit of imaging, and one of which I'd had the beam on the whole time. And so what this is we have different levels of carbon contamination, and it turns out that if you have just a little bit of residual carbon, it can help this evaporation process happen. But if you're using the electron beam, it looks like you're creating a thin film of carbon that's thicker and there all the time and suppresses this phenomena. In other words, you have to be aware of the fact that your electron beam can contaminate your sample and change things about what you're imaging. And so if you have a better vacuum, then you are in better shape, okay? You can help things with this. Again, if you follow proper procedures, if you make sure your sample is clean at the end of the sample preparation process, if you use, say, gloves to make sure that you don't touch past the O-ring, if you're just careful about not touching past the O-ring of the sample holder, that can help. There's another machine that has been brought into use more than 10 years ago now called a plasma cleaner. And what you do is you take your sample holder and you clean it in an argon-oxygen plasma to get rid of the extra carbon on the sample and sample holder, and that can help a lot. We have one of those with the advanced microscope. So that's a real issue. The other thing that we worry about is water, and in fact, one of the other nice things about just getting rid of film in the system is that the film is a piece of polymer. It always has some water absorbed on it, and so if you just remove film, you find that your system's cleaner and easier to pump out, okay? Usually when you're storing your film, you store it under vacuum, but you have to take it out of that vacuum and move it over, and so it does, again, introduce problems with your vacuum. So again, the message, have to get rid of the vacuum, have to get rid of the ions so that the electrons can travel through vacuum, but more important, you really want to have a decent vacuum so that you don't interfere with your imaging of your sample. In particular, this is a problem for analytical microscopy. If you're trying to do small probe work for EDS or EELs, and you put a very intense probe on your sample, it will actually collect the local carbon around there and form a little tower of carbon. And so if you're starting to do quantitative analysis, you will find that your signal yield changes with time because increasingly what you're probing is the carbon contamination as a function. The sample area is fixed, but the carbon contamination grows, and so you end up having more and more problems with carbon contamination affecting your results. So it's, again, important to be clean. Yes, Leor?
If you let the beam raster all the area uniformly, you can avoid it or minimize
So he asks, what happens if you raster the beam uniformly? Well, what you then get is a uniform level of carbon contamination over a square. Well, it's thin, but if you're rastering continuously, it will thicken up as well. If you use the SEM, which again, some of you all take an SEM class, you'll notice that it's not uncommon at all to see contamination local to the area you've been imaging for quite some time. And it's the same effect. It's the residual carbon piling up where you want. And again, one of the things that you can do now is you can buy something called an evacatron. It's a system that just puts in an argon-oxygen plasma in the SEM. Okay? It cleans the whole SEM and your sample. It looks like they're about $15,000, and I'm trying to find a little bit of money to put one over in the Hitachi over at Berk for just that reason. So it just helps clean things up and minimize that problem. But carbon contamination is an issue. So during sample preparation, keep your sample clean. Use gloves when handling stuff that goes into the vacuum. Don't touch past the O-ring in the case of the TEM holder in particular. Use a plasma cleaner if you can. All these things will help you with that. Okay? Okay. So that's what I wanted to say about vacuum.